The researchers are Sheldon Tapin, Imran Mohammed, and this project was supervised by Mr. Ellen Marks, Mr. Malcolm Williams, Mr. Rashad Raj, and Mr. Shalak Bush. What is a unique person data problem? In simple terms, it is the allocation of courses to rooms of particular time slots while satisfying a variety of sort and happens rates. We believe that the existing approaches are falling short in their attempt to optimally solve the university course and data problem. Existing approaches to the problem are constraint-based approaches. In a constraint-based approach, a problem is modeled as a set of variables with a finite domain. The method assigns values to variables that fulfills a number of constraints. For this approach, this can be seen as a three-phase approach. In the first phase, the courses are grouped into time slots to construct feasible timetables. In the second phase attempts to reduce the second-order context by using permutations of the time slots. And the third phase is employed with the aim of improving the quality of the timetable solutions. And third approach are heuristic and heuristic methods. Heuristic is basically a search strategy, whereas method heuristics is an iterative generation process which guides a subordinate heuristic by combining concepts for exploring and exploiting the search space. Learning strategies are used to structure information or to find efficiently near optimal solutions. Limitations of the existing solutions. They are mathematically based in nature. If the problem falls outside the scope of the mathematical formula, then an undesired timetable solution will be an issue. Due to the decomposition and extensive study of the timetable problem, we believe that the existing approaches and the timetable problem are disjointed. The time taken to generate a solution can take very long. And last but not least, at times, the timetable solutions can be generated with clashes. How the concept was arrived at. In order to better understand the timetable problem, it was decomposed into generic entities, relationships, behaviors, sources, and interactions. It was noted that it drew a parallel to a natural system because of the autonomous nature of the entities both in the timetable, both in timetabling and the natural system. Also, it was found that the initial states of the timetable problem is dynamic in nature, but it eventually becomes stable if it is successful in its quest to attain equilibrium. That is, if the problem is feasible. In this regard, the timetable problem can be viewed as an environment in which various entities interact. These entities include courses and rooms of particular time slots. The eventual organization of the structure of the timetable system is governed by a number of roles known as hard and soft constraints. A characteristic of a timetable system would be the need for entities in a timetable to be organized in such a way as to avoid conflicts. Another characteristic is that before an entity makes a decision, it tests its space. It tests the neighborhood space to see if it is safe to occupy. There is also competition among entities of the system for scarce resources in order to bring about a resolution of the rightful ownership of resources. The entity within the system iteratively tests for the aforementioned characteristics and, if possible, rearranges themselves until they are optimally placed in their rightful position within the system. These characteristics and behaviors can also be found in a natural self-organization system. For solution, we propose to apply the principles of self-organization found in biological systems to solve the universal quantitative problem. One would ask, what is self-organization? It is a process in which a pattern at a global level of a system emerges solely from numerous interactions among the lower components of the system. Sorry about that. Self-organization can be seen as an umbrella term that represents many systems. So we choose miselection . So we choose miselection as a principle of our desired principle of self-organization to solve the universal timetable problem. In our system, a course is abstracted to be a male, a room at a specific time slot, female, hard and soft constraints are laws of abstraction, and the timetable search space is the neighborhood or the environment in which a course would search for potential mates. Interactions within the system. Firstly, a male will have to search the environment to find potential mates. If he is attracted to a female, then she will be placed on the potential list of mates. Likewise, if a mate doesn't suit his expectations or his criteria, then he can reject her. But for this one, no, not at all. If no potential mate was found, then of course lower his expectations and searches again. To relate this into the timetable problem, for example, if a course searches for a room and all the rooms are smaller than its size, what he can do is that he can split in half, and that will be represented as two entities, and that can go and search the environment. And this process is repeated until a potential mate is found. So that all entities can mate within the system. When a male finds his list of potential mates, he has to scrutinize to see which is the best suited mate, to see which female he should mate with. Scrutinize both of the mates. She's better than the first, she's not. Then, when you do find the best suited mate, you have to solicit the mate, the female. When he does that process, she has to now check him out to see if he got what she's looking for. Once you got it, you got what I'm looking for, then they can go on. Likewise, there will be a scenario in which a male finds a female or a potential mate but she's already taken. In this case, he will be rejected, but he can ask which is one of it because he would want to compete for her. So she gives him the information, which is one of it. So you have to compete with that male. So there's a process of competition within the system. So if course B wins, or the male that was bonded with her at first, if he wins, then he stays bonded with that female. Or if the other male wins, then the first male will have to go and search again for other potential mates, and he will bond with the female. The static design of the system. The triangles are represented as females and the circles are males. The attraction are the hard and soft constructs. In this model here, this female is bonded with this male. But this male here is rejected from this female. In this case, it is seen that he has searched the whole environment and he didn't find any potential mate. So he must compromise, that is, drop a few constraints. So when you compromise, you can compromise and find potential mates, then bond. Snapshots of the system. This is the master view of the timetable. Basically, all courses of the university in one timetable. This can be broken down into faculties, as this here is the Faculty of Natural Sciences. As you can see here, they do have some amount of knowledge as to choose rooms within their faculties. So they would only choose rooms in the next faculty if the room within their faculty doesn't meet their expectations. Sorry. Likewise, this is a timetable for social sciences. Another feature of the system is that a program can be highlighted. All courses within a program. Also, courses can be highlighted, and lectures also can be highlighted. And these here are features that test that there isn't any conflicts within the timetable. And last but not least, this shows that the lecturer can stipulate when they do not want to teach. So they can say that, hey, I don't want to teach on Mondays or Tuesdays, or they can say periods within a day that they don't want to teach. The data set was grouped into 3 categories, ranging from small, medium, and large. The small category consisted of 100 courses, 5 rooms, and 80 students. The medium and large categories both consisted of 400 courses and 10 rooms. But the medium consisted of 200 students and a large consisted of 400 students. The results, this was the results from the data set was generated using an ANOVA test, which is a statistical test that measures variances. The small data set shows that most solutions completed generation of the timetable in milliseconds, whereas our solution took 0.6 minutes to complete the solution. The median data set showed that our solution outperformed all other timetable solutions in terms of time taken to generate the timetable. And the large data set showed that some solutions took at most 2 working days to complete a timetable solutions, and the others that aren't showing failed entirely to generate a timetable solution. Our solution only took 54.6 minutes to generate a timetable solution. Evaluation of the results. The Harris specs used were different from those used for the existing solutions. Different constraints were taken into consideration, but we still believe that our system may still outperform the others based on the ANOVA test, which proved that our approach is 100% more accurate. I think I got the term wrong. 100% more, I forgot the term, but more efficient than the existing solutions. Limitations of the implemented solutions: it does not cater for lab sessions. However, if a lab session is entered as a course, then it can be go with permits. For example, a computer science lab, it will require computers, projectors. Within those constraints, that it will look for a room with those criteria. Second, if there is not enough rooms for all the courses, then only some courses would be scheduled, and the attentive process can be very tedious. Conclusion: self-organization principles is applicable in solving the university course timetabling problem. We would like to optimize the timetabling problem. We would like to optimize the timetable to accommodate a simple language. So, for example, the person that is doing the data entry can say, I want this course to be scheduled at this time only in human language, not jobless. Secondly, we would like to cater for the scheduling of our sessions, but this can be done. And lastly, the determination of the proximity of rooms, so a faculty that the course belongs to. This is done to some extent. But apart from being within his own faculty, he doesn't know his proximity to other faculty. So, for example, if a course in natural sciences can choose a room in technology if it best suits his requirements over a room in social sciences, even though that's closer. And acknowledgements, we would like to thank God for granting us the health and wisdom throughout the duration of the project. We would like to express our gratitude to Mr. Ellen Marks, whose insights, guidance, and contributions were priceless without, and without him, we would not be able to have succeeded. We would like to thank Mr. Mark Williams, Mr. Roger Gazwaj, and Mrs. Charlotte Blakebridge for providing insightful comments and suggestions. And finally, to our family and friends for their support and encouragement. Thank you.